Hello guys, welcome back. This is our first analysis for heat for regenerative cycle. We have a gas turbine that unit that receives air at 100 kilopascal and 300 Kelvin and compresses it adiabatically to 620 kilopascal with a compressor that has an isentropic efficiency of 66%. The fuel that we are going to inject is 44,186 kilojoules per kilogram, and we are going to introduce the concept of fuel-air ratio or air-fuel ratio. We are going to work both, but the fuel-air ratio it's 0.017 kilograms of fuel per kilogram of air. The turbine internal efficiency is 90%. We are asked to determine the unit, the work per unit mass of the turbine and the compressor and the thermal efficiency. So far it's the same what we have seen, but then we are asked to introduce an regenerator with an effectiveness of 60%. We are asked also to consider pressure drop. For this first analysis, what we are gonna do is neglect it. Let me change this color to be this. So we are gonna neglect this, but pressure drops. At the end, we are going to indicate how to introduce them, and you can repeat the analysis. But what we need to find out is the new fuel-air ratio to the same temperature that we had before. And with this new configuration, we are asked to find out the network and the cycle efficiency. So let's start by having a sketch of what we have. We have our compressor. And we receive, this is our state 1, we receive a mass flow of air, then we go out of this compressor into the combustor. This is our state 2, we have this air, and then we introduce a mass flow rate of fuel. At the end, because of this combustion, we finish at state 3, introduce this into a turbine. State 4, we connect the turbine to the compressor, and we have a net output. So what is different here is that we are gonna introduce, or we are going to use in the analysis the mass of fuel that we are analyzing. So first of all, we are going to do it without, this is without regeneration. And we are not being told, we are going to use variable specific heats. That is table A17. Okay, we can start our analysis state by state. And we know that state 1, seguimos. So we can start only by different states. So state 1 is defined by P1 equal to 100 kilopascal. And T1 equals 300 Kelvin. This leads to a value of H1 equal to 319 and PR1 of 1.386. For state 2S, we use PR2 over PR1 equal P2 over P1, which solving will give us a PR2 of 8.2 59.3, and by interpolation we'll have an H2S of 506.44 kilojoules per kilogram. Now, the isentropic efficiency of the compressor, which is 0.66, is equal to H2S minus H1, H2 actual minus H1, solving for H2A leads to a value of 612.69 kilojoules per kilogram. Now, in order to get H3, we need to perform an energy analysis. So to get and we're going to do it in the next page. So if we go back, we can see that we have two inlets of mass and energy. We have air and fuel, and we have one outlet. So applying first law, and remember that for this combustor, heat and work from or over the surrounding will be zero. We will have something like this: the mass of air times H2 plus the mass of fuel times the heating value, and that heating value is a 44,186. This is all the energy that goes in. So the energy that goes out is the total mass of air plus mass of fuel times H3. Now, dividing everything by mass of air, we'll have H2 plus mass of fuel divided by mass of air, Hc, equals 1 plus mass of fuel, mass of air, H3. Now the air-fuel ratio is defined as the mass of air divided by mass of fuel. That's the air-fuel ratio. So we see that we can substitute here to be what H2 plus Hc divided by the airflow ratio equals 1 minus 1 over airflow ratio times H5. So we can solve for, we know all this will be 1 over 0.017, which is 58.82. So solving for, sorry, this number is wrong, it's not H5, it's H3. So solving for H3 and substituting, we'll have 1,341.05 kilojoules per kilogram, and by interpolation we can find that T3 is equal to 1253.6 Kelvin, and PR3 equals 284.93. So we can define state for S by doing our isentropic relation PR4 over PR3 equals P4 over P3. Sorry, this is, yes. So that leaves the value of PO4 of 45.95, and by interpolation we have H4S to be 812.98. Now, using the efficiency of the turbine to be H3 minus H4 actual divided by H3 minus H4S, and solving for H4 actual, we have that H4 actual is 865.78. So now we know that the work of the turbine is H3 minus H4 actual, which leads to a value of 475.27, and the work of the compressor is 612, is H2 actual minus H1, which leads to a value of 312.50. If we make this subtraction, we have the net work to be 162.77 kilojoules per kilogram. Now Q in will be the 1 over the airflow ratio times HC, which is 0.017 kilograms of fuel per kilograms of air, times the heating value 44.186 kilojoules per kilograms of fuel. We cancel this, and Q in is 751.16 kilojoules per kilogram of air. So the efficiency will be net work divided by Q in, which leads to 0.2167. So what we were asked was the per unit mass work of the turbine, the compressor, and the thermal efficiency. So we know that the compressor 312.5 kilojoules per kilogram. The work of the turbine was 475.27 kilojoules per kilogram, and the efficiency is 21.67%. These are the first values that we that we are getting. And next we are gonna do it with the modify cycle. So now we are gonna so now we'll be with regenerator. In this case, we're gonna modify this scheme and add the regenerator here. We're not gonna change our numeration, so we're gonna start with the compressor again. We have the mass flow there, 0.1. Then we are extracting, passing through the regenerator, and then through the boiler. We'll still have the mass of fluid, and then we go to the turbine. Here, what we're going to do is this is our regenerator. So our states are the same. We are having a state 5 here, and we're going to introduce this state X. So T3, we need to keep the same T2, so is the same value that we found before. With this we have H3 ampere 3 be the same. Now state 1, 2 actual, 3 and 4 actual are not changing. We are only introducing state X. And in order to introduce this state X, we have an effectiveness of 60%. And this effectiveness is equal to Hx minus H2 divided by H4 minus H2. So solving for Hx, we have 764.54. So with this, we can do our energy balance. In the heater, and to this energy balance, similar to what we saw in the video, will be Hx plus Hc divided by Af. It's equal to 1 minus 1 over Af H3. The only unknown is HF, I mean the airflow ratio, so we solve for airflow ratio, and this AF is HC minus H3 divided by H3 minus HX. So this is 74.31, which it's 0.01346 kilograms of fuel per kilogram of air. So we notice that we are saving because formula in the past we have 0.017, so we're using less fuel. That means that our Q in will go down. So this is the first thing that we are looking for. Let me change this color. So it's 74.31 kilograms of air divided by kilograms of fuel. Now, so the work of the compressor is still the same. It's H2 minus H1, and we have it from the previous one to be 312.5. But the work of the turbine is now different because it's not only passing MA, but the work of the turbine will be 1 plus 1 over AF times H3 minus H4A. This signifies that we have more mass passing through the turbine. Solving for this, we have this new work of the turbine will be 481.66. Again, this is kilojoules per kilogram. If we rest, we have our network. Let me write it correctly. Our network will be 169.17. It increases because we have more mass passing through the turbine. And then we have our Q in, which will be HC over our new airflow, which will give us 594.36 kilojoules per kilogram. 594, and we can see that in the past it was 751. So this is the benefit of our regenerator, we reduce the amount of heat that we are providing. We're slightly increasing the network. Because of this, our thermal efficiency increases to 0.2844. So we see that we increase the efficiency of the cycle because of the regenerator. We increase our network, we increase our efficiency. Finally, we didn't we disregard the pressure drop, so we are going to indicate what will be the effect. In order to introduce the pressure drops, we will need to change P3 to be P2 equal P2 minus 20 kilopascal, and P4 equal to P1 plus 3.4 megapascal, since we are having a pressure drop across. And you can see the formulas on the screen, and that will change a little bit the enthalpies because of the PR over the pressure ratios. Well, this is all. Thank you.